Hello, my name is Shoikat Rai. In this presentation, I will be discussing my project simulation of a dynamic voltage restorer for voltage sag mitigation and power quality enhancement. This work was carried out as part of the course ENGI 9857 Instrumentation and Control of Energy Systems at Memorial University of Newfoundland under the guidance of Dr. Mohsin Jamil. A three-phase DBR model was developed in MATLAB Simulink to test its performance under voltage step conditions and observe its effect on overall power quality. Abstract. The project addressed voltage step, a major power quality disturbance by simulating a DBR system with DQ0 based PI control. The model was tested under single line to ground fault, double line to ground fault, and three-phase fault. In each case, the DBR successfully restored the load voltage and reduced total harmonic distortion to below 1%, confirming its effectiveness. Introduction. Voltage spikes caused by faults or sudden load changes can severely affect sensitive equipment. In this study, a DVR was implemented in a three-phase system to mitigate such disturbances. Its effectiveness was assessed based on voltage restoration and harmonic reduction. Literature review. In previous studies, DVRs have been implemented using a wide variety of approaches. Some designs incorporated energy storage systems, enabling support during longer disturbances. Others explored multi-level inverters to improve output quality. Control strategies like artificial neural networks, fuzzy logic, and sliding mode control are also selected to enhance dynamic response and adaptability under varying grid conditions. Despite advancements in DVR design, many solutions require complex hardware or are difficult to turn in practice. In this project, a simpler configuration was chosen, a two-level BSI DVR control with a DQ0-based PI controller. This setup is easier to implement and suitable for testing voltage seg compensation across different fault types. The focus was placed on analyzing voltage restoration and TSD performance using MATLAB simulation. DVR dynamic voltage restorer. A DVR is a series connected device used to inject compensating voltage during sag or swell conditions. It is triggered only when voltage drops below a reference level. In this project, its behavior was modeled and simulated to assess its role in stabilizing load voltage. DVR topologies. DVRs may include or exclude energy storage systems. The model system used a two-level voltage source inverter with a DC source. This approach allows for the injection of both active and reactive power even during severe voltage swings. Components of DVR. The main DVR components included a DC energy source, BSI inverter, LC filter, and injection transformer. These elements were modeled in Simulink to replicate the operation of an actual DVR. Working principle. During normal operation, the DVR remains inactive. When a disturbance is detected, the inverter generates a compensating voltage. This voltage is filtered and injected through the transformer to restore the load voltage to nominal levels. Mathematical modeling. This slide shows the key mathematical tools used in DVR control. Park transformation converts three-phase ABC voltages into DQ0 components, simplifying control by aligning the signals with a rotating reference frame. The inverse Park transformation converts DQ0 signals back to the ABC form for inverter switching. The PI control equation adjusts the system response based on the error signal, balancing a proportional and an integral term to ensure both stability and fast correction. The D-axis typically controls active power, while the Q-axis handles the reactive power. Simulink model overview. This Simulink model represents the overall test system. It includes an 11 kilovolt source, a step-down transformer, the DVR, a fault block, and an RLC load. The DVR is connected in series with the load. Various faults are introduced using the fault block between 0.03 and 0.07 seconds. Voltage measurement blocks are used before and after the DVR to observe the voltage profile with and without compensation. Internal DVR subsystem. This figure presents the internal structure of the DVR. A 500-volt DC source supplies power to a two-level voltage source inverter VSI, composed of 6 IGBT switches. These switches are operated by gate pulses from a PWM generator to synthesize the desired AC voltage. The inverter output is filtered using an LC filter to eliminate high-frequency switching noise. The filtered voltage is then fed into a 12-terminal injection transformer. This transformer allows the series injection of the compensating voltage into the distribution line to correct voltage set during fault conditions. Controller subsystem. This subsystem performs voltage regulation. The measured load voltage is converted into the DQ0 frame using a phase lock loop. The D and Q components are compared with their respective references. Errors are passed through PI controllers and the outputs are transformed back into ABC signals. These are used to generate PWM signals for controlling the inverter. Control strategy flow. This flowchart illustrates the control strategy used in the DVR system. The process begins with the measurement of the load voltage. This voltage is first transformed from ABC to DQ0 frame using Park transformation, synchronized by a phase lock loop. The D and Q components are then compared with their respective reference values. The error signals generated are processed through PI controllers, which determine the required control actions. These outputs are then transformed back into ABC frame using inverse Park transformation. Finally, the resulting signals are fed into a PWM generator, which produces the gating signals to control the inverter switches. This sequence ensures that the DVR injects the appropriate compensating voltage quickly and accurately whenever a disturbance occurs. The results and analysis section begins with the performance of the DVR under different fault conditions. Three types of fault were simulated: single line to ground, double line to ground, and three-phase to ground. In each case, the DVR's ability to restore voltage was evaluated. Case 1, SLG fault. In this first case, a single line to ground fault was applied between 0.03 and 0.07 seconds. The load voltage dropped significantly, but after DVR compensation, the voltage was restored close to 400 volt. The waveform remained stable and smooth with no overshoot after the fault was cleared. Case 2, DLG fault. A double line to ground fault was applied between 0.03 and 0.07 seconds. A sharp drop in load voltage was observed during the fault. After DVR compensation, the load voltage waveform was restored to the desired level. The waveform remained stable with minimal distortion throughout the fault period and after its clearance. Case 3, three-phase fault. This slide represents the voltage profile during a three-phase to ground fault applied from 0.03 to 0.07 seconds. The DVR responded by injecting the required voltage to counteract the dip set. The load voltage returned to nominal levels, and the waveform appeared smooth and stable following fault clearance. FFT analysis. To evaluate waveform quality after compensation, fast Fourier transform analysis was performed on the load voltage. FFT is preferred because it provides a clear indication of harmonic distortion in the signal, which is a key measure of power quality. It allows precise calculation of the total harmonic distortion or TSD after DVR operation. Case 1. In this case, FFT was conducted after fault clearance at 0.08 seconds. The TSD was reduced to 0.88%, indicating that the DVR not only restored voltage but also improved the harmonic quality of the load waveform. FFT analysis case 2. In the DLG fault scenario, TSD was calculated at 0.08 seconds after the fault clearance. The value was again reduced to 0.88%, confirming the DVR's consistent harmonic suppression. FFT analysis case 3. For the three-phase fault, FFT was also conducted at 0.08 seconds. The TSD was found to be 0.90%, which still indicates a strong harmonic mitigation by the DVR even under the most severe condition. TSD summary table. This slide summarizes the total harmonic distortion values for all three fault cases. TSD was calculated after fault clearance at 0.08 seconds. In all cases, the TSD remained below 1%, which confirms that DVR not only restored the load voltage but also improved waveform quality across different fault conditions. Discussion. The DVR system was tested under three types of faults: single line to ground fault, double line to ground fault, and three-phase faults. In each case, the DVR began compensating at 0.03 seconds and continued until the fault was cleared at 0.07 seconds. The DQ0 based PI controller used proportional gain 40 and integral gain 154 for the D axis, and proportional gain 25 and integral gain 260 for the Q-axis. With these values, the DVR effectively injected the required voltage and restored the load to normal conditions. The waveform remained smooth and no overshoot was observed after fault clearance. FFT analysis showed that the TSD remained below 1% in all cases, confirming that the DVR's ability to handle both voltage regulation and harmonic mitigation. Conclusion. A DVR system using DQ0 based PI control was modeled and simulated in MATLAB Simulink. This system was simulated under different fault conditions that caused voltage sag. In each case, the DVR successfully restored the load voltage close to the nominal and kept the waveform stable. After compensation, TSD was also reduced, confirming that the power quality was significantly improved. These results validate the DVR's effectiveness in mitigating the voltage and enhancing the overall system performance. References. This slide shows the references used in this project. This is the end of the presentation. Thank you for listening.